Guys started any of the chapter 9 homeworks?
It's a work in progress.
Okay, well that's honest. Let's go and grab a couple of problems here. And all right. So I just grabbed I'm going to grab a random 9-1 question. And then we'll grab one or two of those and then grab one or two 9-2 questions and just kind of do a couple. All right. So 9-4 says, in each graph, the distance d in kilometers from a starting point for a bicyclist is plotted against time t in hours. And I don't think we're going to answer this for every graph. We're just going to do like one of these, because once you've done it once, that's a good example, and you can try it on your own after that. So it says calculate the average speed and for each bicyclist between the points P and Q by drawing the appropriate secant. What is a secant? Just the line between the 2 points. And then how am I actually going to do the calculation here? I'm just going to do slope. Is everybody okay there? Super easy, right? When we talk about average rates of change, all we're talking about is calculating a slope. Part 2 says, estimate the instantaneous speed at point P for each bicyclist by copying the graph and drawing an appropriate tangent. So again, what I'm going to do is I'm just going to kind of draw in a tangent line. Let's try that again with a little bit finer pen. So maybe like that. So I'll just write slope for the tangent. Looks like the point 21 and then maybe 10, 0. And then part 3 says, are any of the bicyclists not moving at any time during the ride? If so, which bicyclist and during what time interval? Justify your answer. So if you're not moving, what would your velocity or your speed be? 0. So your speed is going to be represented by the slope of these tangent lines that we're drawing. So let's look at graph A. I'm going to erase these marks off of there. Is there any place on there where when I draw a tangent line, it's going to have a slope of 0? No, right? Because there's no horizontal parts to the graph. How about for B? I think if I drew that at Q, that would have a horizontal tangent, right? And then similarly, if I drew the tangent at 0, that'd be a horizontal tangent. So just one specific time. These aren't intervals. Those are just going to be a discrete time period. And then it looks like here at graph C, again at point P, looks like we'd have a horizontal tangent there. Everybody cool? That's all I'm looking for. How'd that feel? Not too bad, right? Just have to like understand the vocabulary, but the actual mechanics of what you're doing is pretty easy. Just doing like slope formulas or whatever, but there's some vocabulary involved that we have to make sure we're comfortable with. Let's do one more of these. Let's say we grab this one. This is still from 9.1. Says the points A, B, and C lie on the graph of y equals e to the x as shown. I guess let me grab the graph because they do give us a graph here for this. I didn't copy it though. I gave you this tiny little picture. I had to blow it way up. Estimate to 3 significant figures the slope of a line tangent to the graph y equals e to the x at each of the points A, B, and C. And then use your graphic display calculator to approximate the values for 1 over e and e. Comment on your results. I'm going to tell you real quick. I know what's going to happen. So we would do, I'm going to do that tangent line, right? Guess what the slope of that's going to be approximately? 1 over e. And then I'll do this one. The slope of that one's going to be approximately 1. And then we'll do this one. That slope's going to be approximately e. Here's the $1 million question. Can you look at these results and tell me if f of x is e to the x? What's the equation for the derivative going to be? So what we've shown here is when x is -1, the derivative was 1 over e. When x is 0, it's 1. And when x is 1, it's e. We're not multiplying by e. Well, kind of, I guess we are. But what would the function look like? What's the equation for that going to look like? Let me give you a hint. What if I write 1 over e as e to the -1? What if I write 1 as e to the 0? What if I write e as e to the first? Yeah. The derivative of e to the x is just e to the x. That's what they were hoping for you to see there. I cut out the annoying parts and just went to like, what were we supposed to observe? Because in here, I'm going to tell you this real quick. No one is going to compute the value of a derivative graphically unless all you have is a graph. Just no one wants to do this. If you have an equation for it, we're just going to do this algebraically. We just haven't gotten that quite that far yet. All right. Let me grab a 9-2 question, then we'll get on with the show. Sound good? So this is a 9-2 question here. And like all your favorite of these IB book questions, there's like 100 parts to it, right? Don't you love it? Like, oh, there's 5 questions. And look, each 5 of them has like 16 parts. It's like this homework will be quick. Oh, no, it won't. All right, so this problem says a runner goes for a long run in the mountains, covering 25 kilometers in 5 hours. Her distance is described by the function d of t equals yada, 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 where d of t is kilometers and t is hours, with t between 0 and 5. The derivative function is given as d prime of t equals yada, yada, yada. It says find the distance covered after 2.5 hours. How am I going to calculate that? Which function do I want to use, d or d prime? D. So what am I going to do to d to get the distance covered in 2.5 hours? Plug 2.5 in for t, right? And I'll leave that to you guys to type in your calculator. Well, actually, let's do this. Let me show you. If you're going to be using your calculator to, or you have like an equation on your calculator, and especially if it's got like stuff that's going to be annoying to, if you're going to be plugging stuff in all the time, and if it's going to be kind of an annoying thing to plug in because there's like 3 spots or 4 spots or something to plug it in, I would consider doing something like this and just typing your function into your y equals menu like this, and then exiting out and doing that vars, y vars function y1, and just doing like that. So it looks like about 17.7 kilometers covered. Everybody's okay there? Says verify the runner completes 25 kilometers in 5 hours. How do I do that? Yeah, we're going to plug 5 into D and just make sure we get what? 25. So there's the benefit of like what I just did, because it's super easy to like plug a bunch of stuff in if I'm going to have to plug in values after value after value. Doing it this way is like really kind of time consuming, or less time consuming and a lot less annoying than having to like type this stuff in over and over and over again. Says find the runner's average speed during the first 5 hours. When you hear the word average, what are we doing? Slope. So what am I doing? the distance for covered in 25 hours minus 0, or you know, get what I'm saying, right? So 5 kilometers per hour. What should the unit be for the d prime of t? D is in kilometers. Right, if I drew D, it's kilometers and then hours, right? It's like our graph of D. Well, it's going to be increasing, right? D prime is like the slope, so it's going to be y over x. So the unit should be kilometers per hour, right? The derivative of position is velocity. What's going to be the derivative of a velocity graph? Acceleration, right? And the units on acceleration would be like kilometers per hour squared, or kilometers per hour. You could write it that way as well. Okay. Now part E says find the runner's speed at the start and end of the run. So which function do I use to find the speed? D or D prime? D prime. So what is the time for the start of the run? 0. And the speed at the end of the run would be, I'm plugging in what t? Not 25, that's how far I went. 5, that's how long it took me to do it, right? 5 is the time. So when I plug 0 in, I get 35 over 2. Well, let's write it as, 17.5? And again, since this appears to be something I might have to do a couple of times, I'm going to type it in over here in the y equals menu so I can use my calculator to just plug the values in. And then I have 9.17. Okay. Part F asks us to find the time when the runner is going the fastest, and then what is that maximum speed? What would I do to do this? Graph what? D or D prime? D prime. And what am I looking for on the graph of D prime? You're looking for the absolute maximum, right? So I'm going to reformat my graph to go from 0 to 5 on x, and then maybe like 0 to 20 or something. Hit graph. So where's my absolute maximum at? At t0, and that speed is 17.5. Is that okay? Alexis, you're ready to ask a question.
Yeah, what's the difference between D and C?
So d is a function that describes the distance this person's traveled at over some time t. And d prime is describing the speed at which they're going at some time. So here we're showing us we start off going fast. Maybe our mountain run was downhill to start, right? And then we start going uphill almost immediately because we start slowing down right away. Here, we're probably at the steepest part, like cresting the top, and then we start speeding back up because apparently it's flattening back out or becoming a little bit more downhill, or maybe we're just getting a second wind or something. Like, ooh, did the hard part. Then it says find the runner's minimum speed and the time when that occurs. What am I looking for there? How am I going to find the minimum speed? The lowest point on the same d prime graph, right? So to do that, I'm going to do second trace, pick that minimum command. There, it looks left of the minimum. Move that guy over here. That's right of the minimum, enter. So the time is 2.92, and that minimum speed is, I can't really read it because everything is in the way. That's super annoying. Let's do that. There we go, 0.486 or 0.49. Oops, that was supposed to be a 6 there. How's that feel? It's okay? All right, let's move on now into 9.3. But that's a lot of what your homework feels like. As we go deeper, the homework should be getting less annoying and less tedious because it's going to become more like, instead of drawing a graph and or drawing a tangent line and trying to approximate its slope, we're going to actually just calculate the values using an equation or something, or a function. All right, so we're going to be talking about interpretations. So the first thing we're going to do is talk about what we can tell from the sign of the derivative. Just drop this in rather than me copying it. So again, f prime of x is just the derivative of some function f. If that derivative is positive, that means the slope is positive, so the function is increasing at that specific value of x. Graphically, what does increasing look like? Like if you're walking along the graph, you're walking uphill, right? If the derivative is 0, the slope of the function is 0 there. That means the function is constant. It's neither increasing or decreasing. What does a constant function look like? Horizontal line, so it'd have a horizontal tangent at that point. Or the graph could be horizontal for like a section, right? All the tangents on that section then would have slope 0. And then if the derivative is negative, the graph or the slope is negative, So it means the graph would be decreasing. What's that look like? It means like if you're walking along the graph, you're walking downhill. And when we walk along a graph, we're always walking from left to right. Everybody feel good on that? So let's say we have the derivative x squared minus x minus 12, and we want to identify where the function is increasing and decreasing. To do that, we need to find where the derivative is positive and where it's negative. Would you agree? What's going to be the easiest way to do this? Easier than that. Easier than that. Graph it on your calculator. What are we looking for when we graph this derivative on our calculator? We're not this is representing the slope of the function, right? The derivative is representing the slope of the function, but we're asking the question where the function is increasing and where it's decreasing. So what slopes correspond to increasing? Positive. So what are we looking for on the derivative graph to represent a positive slope? What does the graph have to look like? Has to be above the x-axis. So you're looking for where the derivative is positive. That'll be the same thing as where the slope is, right? So this part of the graph would correspond to f being increasing. And this part of the graph would correspond to f being increasing. I did zoom standard, is what I did to just like reset my window back to something sensible. So, yes.
So even if it's going like down, like from left to right, it's going down, it's still increasing above.
So, yeah, let's be clear here. What you're looking at is the graph of f prime, right? When f prime is positive, f is increasing. We don't know what f looks like other than what we can interpret from the graph of its derivative. Does that? And that's the hardest part for students right away, is you're talking about what can I learn about from f prime that I can say about f that maybe I can't even look at, right? We don't know anything about f other than what we can interpret from the graph of the derivative, which we do have access to. Now, if we do this long enough, you'll be able to take that derivative and create f from it, but we're still like a chapter 2 away from being able to do that. It's not hard, but we're a ways away from doing that. So what I'm going to look for is simply where the graph is crossing the x-axis, right? Because you know everything before this point is positive, so the graph f should be increasing. Everything between this point and this point is negative, so f should be decreasing there. And everything after this point, f should be increasing. Everybody cool? So I'm going to do second trace and use the 0 command. So one of my zeros is at -3. And then I'll do second trace, 0 command. Hi, Aiden. Okay. Left bound, right bound, guess, and then 4. So we're increasing from negative infinity to negative 3, and then from 4 to positive infinity. And then we're decreasing from negative 3 to 4. And usually we'd write these using like interval notation like I've done here. So again, we're describing the x's where f is increasing or f is decreasing. Everybody's cool? And again, we can say this because f prime is greater than 0 there, and because f prime is less than 0 there. What if we wanted to do this algebraically? So I would want to be interested in where this thing is equal to 0. So to solve this equal to 0, we could factor, we could use the quadratic formula. Both of those things I heard mentioned, those are both good ideas. So this factors to x minus 4 and x plus 3. That gives me the zeros 4 and negative 3. So if I draw like a number line, I'm concerned about what's happening when it's less than negative 3, between negative 3 and 4, and then greater than 4. To figure out what's happening, I'm just going to pick a test value. So I'll pick something that's less than negative 3, say negative 4. Pick something between negative 3 and 0, or negative 3 and 4, say 0. And then something that's bigger than 4, say 5. And then what I'm going to do is I'm going to compute f prime of negative 4, and then f prime of 0, and then f prime of 5. So f prime of negative 4 is 16 plus 4 minus 12. That's positive. I don't really care what the number is, I just care the sign of it. If I plug 0 in, that's 0 minus 12. Well, that's a negative. And then if I plug 5 in, that's 25 minus 5 minus 12. Well, that's positive. So I see that, again, we're positive when we're going from negative infinity to negative 3. We're negative going from negative 3 to 4. And then we're positive again going from 4 to positive infinity, which matches up exactly with what we set up there, right? Do you guys feel okay on how we did that both ways? Again, you always have access to your graphing calculator on your IB exam, so if you're able to use the graphing calculator well, it does most of the work here for us. In your situations, that would be the method that I would use. But again, that's a comfort level thing. All right, let's do another example. It tells me the rate of change in a population is given by the function dp dt equals 4 over t plus 1, where p is the population in thousands and t is the time in years, where time is greater than or equal to 0. Find the initial rate of change in the population. Rate of change is, when I hear that word, I'm thinking derivative. So what I want is I want my derivative dp dt evaluated when t is equal to what? 0. How did you get the 0? Yeah. I don't know what this population is of, so it's just 4,000 thingies, whatever those thingies are. I don't know if it's people or wolves or unicorns or fairies or leprechauns or what, but everybody's good there? Okay. Describe how the population changes over time. What would I do there to do that? I would want to look at the graph of the derivative, because that's going to tell me how that'll give me a visual of the rate at which population is changing, right? The bigger the derivative, the faster the population is changing. The smaller the derivative, the less the population is changing, or at least the closer to zero the derivative gets, the less the population is changing, right? If it ever becomes negative, I know the population is going to be decreasing in size. There must have been like a plague or something going on. But that's my plan, is I'm just going to take this graph of the derivative and kind of look what's going on. Now I'm going to reset my window here. So I know that my x minimum is 0. And then maybe I'll go for like 20 years or something, I don't know. The y is the value of the derivative. We know it's going to be at least 4. And I know that if t has to be a positive number, 4 over t plus 1 has to be positive also, right? As long as t is restricted to be a positive number, which it says right here. I know that 4 over t plus 1 has to be positive. So maybe I'll just go like 0 to 10 or something. And then I'll just hit a graph. So what are we seeing here? How would we describe what's going on? Okay, we would say hold on, it isn't specific enough. We would say the rate of change for the population then what? It's not negative. Those are still positive values, right? Because they're still above 0, because this is the graph of the derivative, not the graph of population, right? So it's just the rate of change for the population decreases, right? Because it's getting smaller. That rate is getting smaller. What do you notice that's happening, though, eventually to that value for the derivative? It's approaching 0, right? So we can say as t approaches positive infinity, the rate of change for the population approaches 0. Now, read carefully part B on what the directions say. Have we actually talked about the population at all? Not really, right? We've talked about the rate of change for the population. So let's maybe do a better job. This was fine as a first attempt. I just kind of let you guys go. Okay? So here, the point is that this was always positive, right? The rate of change was always positive. You guys agree? So what does that tell us about the population? The population is increasing for all t greater than or equal to 0, but as t approaches infinity, what is happening to the population?
Growth slows down.
More specifically, though, it even becomes not negative, 0, right? As t approaches infinity, the population just is going to stop growing at all. It's okay, man. Again, the hardest part of this is getting used to going back and forth between what the derivative tells us about the function, what the function, and what that means regarding to the function. Or if I look at a function, what does that say about its derivative? That's the hardest parts. And that takes a little bit of time to kind of get used to. So like keep on developing your intuition. Answering and being wrong is okay. That is how we develop intuition, right? How we get used to like, okay, what does this really mean? What does this really mean? What does this really mean? Like in the context of a problem. Everybody feels okay? Okay. All right, let's see. Do another example here. I love how your textbook will do this. Like, hey, here's a question about a graph. Guess what graph you get to look at? Is like this itty bitty little tiny wiener graph that we're going to stick to the side that you can barely look at. It's like, paper is not that expensive, man. Like, make a hardcover textbook and just have some pages in it. It's okay. All right. So it says the graph of the derivative dy dx as shown. Write down intervals where y is increasing and intervals where y is decreasing. So when we're looking at the derivative, what part of the graph of the derivative is going to tell us where the function is increasing at? Above the x-axis. So I have this section, and this section. Everybody agree? Where is it going to be decreasing at? Below the x-axis. So y is increasing from a to b, and then b to d, and then d to, I guess we'll say positive infinity or something. Oh, I'm sorry, that's e to positive infinity. And we'll say it's decreasing then from negative infinity to a, and then b to c, and then d to e. Everybody okay with that? Okay. That feels good to me. That's it for 9.3. Here's what I've been waiting for, finally. 9.4. I think just 4. At least the quiz. Okay. This rule that I'm about to write down is going to be one of the few derivative rules that we're going to expect that you know. Would be on the formula sheet, but you're going to use it so much you're going to memorize it anyways. This is called the power rule. And it's going to be something you'll use almost exclusively in doing the 9-4 homework. This says, for a function of the form ax to the n, the derivative of it is going to be a times n to the x, or times x to the n minus 1. Let's do some examples. Oops, I want to do one other rule here before example. It's fine. Yeah. I'll just do it in Granicus when we get to it. It's fine. All right. Whole bunch of examples here, right? Ugh, come on now. I didn't want to do this. Stop. Nobody wants to do whatever the heck you're thinking of trying to do there. All right. We have y equals x to the 4th. How would I write the derivative of y? What am I going to write to represent the derivative of y? So it's, okay, so we're going to have equals 4x to the 3rd, but what do I write here in this spot? What do I call the derivative of y symbolically? I could write it as y prime. What other way could I write it? Well, it's not f, right? It's y. The other way we might write it is dy dx. So either one of those would be fine. And Megan's correct. The derivative of x to the 4th is 4x to the 3rd. Where you take the exponent, you make it the coefficient, or multiply it to the coefficient, and we subtract 1 from the exponent. Everybody feel good? Okay. Okay. What's the derivative? What should I write here for part B? Y equals 10x squared. Someone other than Megan. You're doing wonderful, Megan. How do I start? Fantastic, right? He took the 2 in the exponent, multiplied it to the coefficient, 2 times 10 is 20, and then subtracted 1 from the exponent. 2 minus 1 is 1, and we don't need to write x to the 1st, we can just write x. So far, so good? Here's a tricky one. Yeah, right? What do you do if there's no x? Think about it. Here's your hint. Think about it. Think about it this way. Okay? What's the graph of y equals 15 look like? It's a horizontal line. What's the slope of that line anywhere? 0. So what should the derivative be? 0. Right? How does that jive with our derivative rule? I can always think of an x to the 0 there. But you can't do the subtraction for whatever. It's just like, don't think about it that way. Think about it like I talked about the graph, where it's just a horizontal line. The derivative of a constant is always 0, which is lovely, right? I love that. D. What should I write here? Great. Or you could write it as -2 over x cubed. That would be fine also if you wanted to not have a negative exponent, but the negative exponent is fine, not wrong. Okay. How should I write the derivative now since it starts f of x instead of y equals? Great. Love that. And then when I actually do the derivative of -1/3 x cubed, what do we get? I'm just going to write -x squared, but yes, it's -1 out front is fine, right? Not wrong. It's equivalent. We don't need the 1 there, so I'm not going to write it, but still good. Okay. So we have s is equal to -5t squared. What do I write here? Good. What other way could I write this other than s prime? Yeah, ds dt. Everybody's cool? Okay. Okay. What do you notice that's different about G here? Oops. They did this. I hate that they called letter G and then all of a sudden changed to G of X. I just was like, I hate that. Okay. So yeah, what do we notice that's different about our G of X here? Yeah, there's addition and subtraction of other monomial terms, i.e. this is a polynomial, right? And the previous things were all monomials, well, except for D, which is not a monomial because it's got a negative exponent, but whatever. Here's the rule. If you have two functions that are added or subtracted, we can use this rule. So if h of x is f of x plus g of x, the derivative of h is just the derivative of f plus or minus the derivative of g. What does that tell us? That this derivative operation distributes across addition and subtraction. So to do the derivative of g here, we can just go and do it like term by term. So the derivative of x to the fourth, the derivative of negative x or -1/3 x cubed, the derivative of 10x squared, and the derivative of 15. And you don't have to write the 0 if you want, right? You guys feel good about that? So no big deal if you have something like, oh no, look at all that stuff. It turns out that stuff doesn't really matter, right? All right, I'm just going to copy it. All right, let's look at H. What do you notice that's weird here? Yeah, the fraction with the x in the denominator. Very good. Do I have a rule, a derivative rule on how to deal with a fraction with an x in the denominator? No, right? The only derivative rule I have is stuff that looks ax to the n. How am I going to deal with 8 over x? Nope. What? Yeah, we're going to make that x to the negative 1. We're going to use our rules of algebra so I can rewrite that in a form that my derivative rule applies. This is critical to all of calculus problems, like numeric, just kind of like grind it out, do the derivative things, is doing some algebra beforehand to make sure that we can use a calculus rule to do the derivative. Okay, so what do we get here when we actually do the derivative? The x to the 0, right? Which is just 1, which doesn't need to be there, right? So we can just write minus 4. And what does this last one become?
Negative 8.
Or if you wanted to, you could write it that way. Either one is fine, though, right? Both of those would be okay. All right, our last example here in this little block. What do you notice right away? The fraction, and the x is in the denominator, right? If I have a fraction where the x is in the numerator, no big deal. That's just a constant times x, right? How am I going to rearrange this so that I can do my derivative rule on it? Yes, that would be okay. I would think about it this way, where you have like, just break it into 2 fractions with the common denominator. So that first part reduces. X squared over x is just x. And then 5 over x can be 5x to the negative 1. We'd get the same thing if you did what you suggested, though, Isaac. So that was a great suggestion. That's exactly right. Not the way I would have thought about it. I think this way is a little bit easier conceptually for everybody else, but you're right on. Exactly the right thing to do. And so what's our derivative then? What's the derivative of x? One. Yeah, exactly. Very good. And then the derivative of 5x to the negative 1. Great. Or you could write it this way. Either is okay, though, right? Both of those would be okay. What do you think? That's it for 9.3 and 9.4. You've seen the big ideas. You want to grab a example from the textbook, do it a couple more, or do a homework problem or something on this section. We got some times, right? I guess we are going to have the chapter 9 quiz next class. I'll make sure I get a quiz description in the OneNote here. All right, so we have a tennis player hits a ball straight up. Why would they do this? I do not know. The height of the ball above the ground is described by the model h of t equals yada, 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 where h of t is the height in meters at time t in seconds after the ball is hit. Find h prime of t, including units, and interpret its meaning. Okay, let's start with the easy part. What's h prime of t going to be?
Use the power law.
Yes! Negative 9.8 t. Anything else? Don't need it. This is good. You're done. You could have been like, yep, that's good. I was just checking to make sure. That's great. What is the unit going to be on h of t, or h prime of t? Meters per second. Very good. And what does h prime of t mean in the context of this problem? I would use the word velocity. What's the difference between speed and velocity, folks? Does anybody know? Yeah, velocity has a direction component to it. So negative velocity means it's moving backward. Speed is the same regardless of direction. You know. So just say that's the velocity of the ball at time t. Everybody feel okay there? I don't know if they would ding you on if you said speed and not velocity. Again, first year teaching this course in a couple of years, so I'm not sure how they're grading these things. But this is probably a good indicator that they'd probably be specific. It says find the velocity of the tennis ball after 1 second, or 1 second after it's hit. So that's just going to be h prime of 1, right? So 6.2 meters per second, right? Negative 9.8 plus 16. At what time is the tennis ball descending at a rate of 10 meters per second? How am I going to find that? Okay. That's what you say. Read the question one more time. Yeah. Descending means the ball's coming back down. Velocity has a direction component. That should be negative. Down is negative. Everybody feel good? So to solve that, I would subtract 16 from both sides and then divide by negative 9.8. Oops. Sorry, 26. Everybody's okay? So it's about, oh no, it's not. So like 2.7 seconds or something. Just guessing. At what time is the velocity of the ball equal to 0? How would I do that? At what time is the velocity of the ball equal to 0? Just doing that, right? So I'd subtract 16 from both sides and then divide by 9.8. It also asks, what is special about this point? Great. So the ball reaches its max height at this time. Everybody agree? Okay. Part E says, find the maximum speed of the tennis ball and the time at which this occurs. How would I do that? I would graph h prime of t. Okay. And then this is really just going to be from 0 to 26 over 9.8, right? Because once the, oh no, that's not what I want. We don't know what it's going to be. I'm just going to put a 5 there or something. That's really fun. What's the maximum speed at? Oh, ooh. Says maximum speed, right? So you want where, not velocity, you want where the absolute value of h prime of t is max. Why the absolute value? Because speed can be positive or negative, right? I'm sorry, speed is always a positive value, whether it's going up or down. That's what I mean to say. I was unclear. Okay. What do I have to be careful about when looking at this graph? Right, the ball is going to you hit the ball straight up. Is it going to keep going down forever? No, man, it's going to hit the floor eventually, right? How long is it going to take to hit the floor? Twice the amount of time it took to get to 0. Right? What comes up must come down. It's going to come down at the same rate it went up. Everybody buy that? So it's really going to be the same as if I did this as just a straight velocity problem. So it looks like 16. That's what it looks like to me. What do you guys think? It's all right? Again, the calculation's pretty easy. Understanding what's going on and making sure you're using the derivative or the function and using those appropriately. That's the hard part. It's just the understanding what's going on part. So you really need to try the problems, okay, to work through some stuff, because it is not trivial to work through the story problems. Like they're eventually gonna get easy. Like none of this stuff took a lot of time for us to calculate, but figuring out what to do, you just need some experience. You need some practice. You need to hear how the problems are presented. You need to look at what to do, figure out when you need the derivative, when you don't, right? So it just needs a little bit of practice there. Okie dokes. Okay, I'm going to stop.